We're going to look at two of the other main components of the tuning preparation. The first component is the semitone width and root, and the second is what we call the absolute tuning keyboard. So let's start with this part here. Semitone width and root, it does what it says. It sets the width in cents for a half step, or the space between each adjacent key. So this is an equal tempered chromatic scale. Each half step, each semitone is 100 cents. However, with this we can set it to be whatever we want. So let's say we want this to be a quarter tone keyboard. I'll set it to 50. Now, so you'll notice down here when I play this, I'm going to adjacent keys. I get to an octave, but it's actually only really a tritone because we've only gone a quarter tone for each half step there. Okay, so super quick way to get a quarter tone keyboard. Another aspect of this is setting the root, and the root basically just tells bitKlavier what note do you want to be as you expect it to be. So in this case, C4, middle C is going to sound an actual middle C, so about 261 hertz. Every other key on this keyboard is going to sound something else. This key looks like it's a C, but it's actually an F sharp. So this is the only one that's correct. If I set it to A440, now when I play this C, it's going to be different, because now the A, we can see A is a proper 69, whereas now the C is much higher. If I set it back, now the C is a proper C. So that's how you anchor this quarter tone keyboard. But you could set this to any number of other widths. So in the last tutorial, we looked at Georg Friedrich Haas's limited approximations. And in that piece, he basically uses what's called 72 EDO, or 72 equal divisions of the octave. So if you do that, you're setting the semitone width to be 16.6667 cents. So now we can try this keyboard that way. So with 72 equal divisions of the octave, you can actually very closely approximate many of the overtones in the overtone series without actually using the precise ratios. You just have such a fine grid that you can get very close. So this is like the Haas limited approximations, but all in one single keyboard. However, it's not really going to be playable like the Haas, because obviously in the Haas you've got 6 different keyboards, so each pianist can play the way they normally do and get the same sort of intervallic relationships. Whereas here, if I play the lowest note of the keyboard and the highest, we can hear it's just barely more than an octave because the keyboard, each key is so small. Another example is 31 EDO, or 31 equal divisions of the octave, which is one that's interested composers and instrument builders for centuries, actually. And there are even split keyboards built back hundreds of years ago that do 31 equal divisions of the octave. So that would be 38.71 cents per semitone. Okay. One thing I want to mention. Oh, actually, before I go on to that, basically you can, if you want an equal number of divisions of the octave, all you do is divide 1200, which is the number of cents in the octave, by the number of divisions in the octave. So in the case of 31 EDO, 1200 divided by 31 is equal to 38.71. So that's where you get that number if you want to do that for any other equal division of the octave. Now, one curious thing about this, and I'm going to set this back to an quarter tone keyboard here, is that this is actually overlaid on whatever tuning you set here. Right now I have it to equal temperament, but if I set it to, say, adjust intonation where we expect the major third to be a little bit smaller than an equal temperament. These values, actually let me step back to this for a second. If you monitor these values when I play a chromatic scale, oops, sorry, I did this wrong. Go back to equal temperaments. Right, you see that they're all integers or 0.5 because they're quarter tones. If I set it to just, you'll notice actually they take on some different numbers. And what's interesting is that these two things are actually overlaid. So if I play a major third, which is actually, instead of 4 keys, is actually 8 keys. So it feels like a minor sixth on the keyboard, but because it's a quarter tone keyboard, it sounds a major third. You'll notice the major third, instead of being an interval of 4, is actually 3.863, which is a just tune major third. So this is overlaid on this, trying to retain the intervallic tuning structure of whatever tuning system you have there. So that's something that could yield some interesting results if that's something you want to explore. Okay, I'm going to set it back to equal temperament. And I want to look at one other example of using this semitone width, and that's for the so-called Bowlin-Pierce scale. And we're going to look at this in the second half of this tutorial as well. And in the Bowlin-Pierce scale, instead of dividing the octave, so 1200 cents, by an equal number, in the equal tempered version of the Bowlin-Pierce, we actually divide the tritive, it's called. So it's an octave plus a fifth. So a 3 over 2, or really 3 over 1 ratio. So instead of 2 over 1, it's 3 over 1 ratio. We divide that by 13. I'm not going to explain the whole rationale behind that, but there are some really interesting things that come out of it. And you can do some research on the Bowlin-Pierce scale if you like. But so that means the tritive is an octave and a fifth. And so if you take a just tuned tritive, that's going to be 1902 cents. So 1902 cents instead of 1200 cents. And you divide that by 13, what you get is 146.307 cents per semitone. So now you'll see when I play 13 tones, because like I said, it's the tritive divided by 13. So I play the C, and then I play the so-called D sharp above, or D flat above that, 13 tones. We get that tritive, 19.02. Okay, so 19 is the octave in a perfect fifth. So this is now, you see that each half step, so-called half step, each semitone is 1.463. Uh, 1.463 or 146.3 cents. So that's something we're actually going to come back to when we look at the absolute tuning and its scala. I'm going to set that aside for now. Talk about two other things with the semitone width. One other thing that might be interesting is just doing some subtle octave stretching. So if you're not familiar with the notion of inharmonicity with the piano, it's something you might want to check out. Basically, the idea is that the overtone series on a actual piano, the actual physical strings, they're not actually perfect ratios, perfect multiples of the fundamental. They're slightly stretched. And so piano tuners, when they tune a piano, they will stretch those octaves, especially at the low end and the high end of the keyboard, so that they're slightly greater than 2-to-1 ratios. So that can result in a fundamental on a low note of a keyboard that sounds actually, it's audibly lower than what it might be if it was perfect 2-to-1 ratios. So I can emulate that here by having the semitone width. You'll see here the interval I'm playing an octave, but it's slightly greater than an octave because of this semitone width. Now this piano sample library already has stretched octaves in it. So we wouldn't want to do this for a piano because this already has stretched octaves. If you do an audio analysis of that, you'll see what I mean. However, let's say you're using a synth as well that doesn't have stretched octaves, and you want the stretched octaves of the piano to match the synth. Well, you could stretch the octaves in the synth so that its tuning actually matches the stretched tuning of the piano. That might cause other problems, like the octaves in the synth itself might sound funny, but it could be something worth exploring. Okay, so one last fun thing to talk about with semitone width, and this gets to something that I find quite interesting about bitKlavier. You know, bitKlavier, sure, it's a piece of software, but its design is completely tied in to the keyboard, the traditional keyboard, and to the whole notion of the physical technique that's used to play the keyboard. So one thing you can do is you can make the semitone a negative number. So make it minus 100. Now watch this keyboard down here as I play an ascending scale. So I'm playing up and the scale goes down. And then I go play down. And that feels so incredibly strange because in my body I'm used to playing my hand going up and the pitch going up. So it really kind of messes with my wiring. And that to me is actually quite interesting. There might be a musical application for this that could be of use to somebody. For instance, you could overlay two different direct pianos. In fact, I'm going to do that right now. And one of them will have a regular tuning attached that will go up, and the other one will have this one. And I'll play just with one hand an ascending scale. So it's one hand, just playing one scale, and I get that nice mirroring, that nice spread there. So some fun things you can do just with semitone width and root.